On the morning of November 23, 1943, Captain Yoshio Hinoki stood inside a secured hangar at the Tachikawa Army Air Arsenal, approximately 40 kilometers west of Tokyo. Before him sat an aircraft that should not have existed in Japanese hands. Republic P-47D Thunderbolt, serial number 42-8877, olive drab paint, white stars on the wings, the words Bonnie painted beneath the cockpit. The aircraft had belonged to Second Lieutenant Paul Gambonini of the 348th Fighter Squadron. Gambonini was now a prisoner, captured 3 weeks earlier after being forced down near Wewak in New Guinea. His aircraft had been recovered intact, shipped to Rabaul, then flown to Japan aboard a transport ship. Now it sat under Japanese fluorescent lights, surrounded by engineers who were about to discover something that would confirm their worst fears about American industrial capacity. Hinoki was not a test pilot. He was a propulsion engineer, educated at Tokyo Imperial University, specialized in aircraft engine design. He had worked on the Nakajima Homare engine, the Mitsubishi Kinsei, and had consulted on nearly every major Japanese aero engine program since 1938. His job today was not to fly the Thunderbolt. His job was to examine its engine, measure it, document it, and explain to the Japanese Army Command how the Americans had built a fighter aircraft around an engine that weighed more than an entire Japanese fighter. The numbers were already known from intelligence reports. The Pratt and Whitney R-2800 double Wasp engine in the P-47 weighed approximately 2,400 pounds as installed. The complete Mitsubishi A6M Zero fighter weighed approximately 5,500 pounds fully loaded. That meant the Thunderbolt's engine alone weighed 43%, as much as Japan's most successful fighter aircraft, complete with pilot, fuel, ammunition, and all systems. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Hinoki walked slowly around the P-47. The aircraft was massive compared to Japanese fighters. It sat heavily on its landing gear, the enormous radial engine dominating the forward fuselage. The propeller was a Hamilton Standard constant speed unit, over 12 feet in diameter. The cowling was huge, covering 18 cylinders arranged in 2 rows of 9. Everything about the aircraft suggested brute force rather than elegance. Japanese fighter design philosophy had always emphasized lightness and agility. Remove unnecessary weight, sacrifice armor for maneuverability, build aircraft that could outclimb and outturn anything the enemy fielded. The Zero embodied that philosophy perfectly. It was fast, agile, long-ranged, and deadly in the hands of a skilled pilot. But it was also fragile. A few hits from heavy machine, guns would tear it apart. Pilots had no armor protection. Fuel tanks had no self-sealing capability. The Thunderbolt represented the opposite philosophy. Heavy armor, heavy armament, heavy engine, heavy everything. The aircraft weighed over 13,000 pounds at maximum takeoff weight. That was more than twice the weight of a Zero. American designers had not tried to build a lightweight dogfighter. They had built a heavily armed, heavily protected fighter bomber that could absorb enormous punishment and keep flying. Hinoki had read the intelligence reports from pilots who had engaged P-47 seconds over New Guinea and the Solomon Islands. Japanese pilots described the Thunderbolt as nearly indestructible. 20mm cannon shells that would explode a Zero often just made holes in the P-47's thick skin. The aircraft could absorb dozens of hits and continue fighting. Some damaged Thunderbolts had returned to base with cylinders blown off the engine, with control surfaces shredded, with fuselage skin torn away, and the pilots had walked away without injury. That level of survivability came from weight, heavy armor plate behind the pilot's seat, bulletproof glass windscreen, self-sealing fuel tanks, redundant systems, structural strength far beyond what was strictly necessary for flight. The Americans could afford the weight because they had an engine powerful enough to carry it. The R-2800 produced 2,000 horsepower at takeoff power. Some models with water injection produced over 2,300 horsepower. That was nearly double the output of the Nakajima Sakai engine in the Zero, which produced only 1,130 horsepower. The power-to-weight ratio of American engines was not dramatically better than Japanese engines. What was different was the absolute scale. American designers had built an engine so large and so powerful that they could hang tons of armor and weapons on the airframe and still have a fighter that could climb, dive, and fight effectively. Hinoki approached the engine, cowling. Two Japanese mechanics stood ready with tools. Hinoki gestured, and they began removing the cowling panels. The cowling was secured with quick-release fasteners, designed for rapid maintenance access. Japanese aircraft used similar systems, but the scale here was different. Each cowling panel was heavy, thick aluminum, carefully formed to provide streamlined airflow while allowing easy removal. As the panels came off, the R-2800 engine was revealed. 18 cylinders, each with its own cooling fins, each precisely machined from forged aluminum. The cylinders were arranged in 2 rows, the front row slightly offset from the rear row to improve cooling airflow. Each cylinder had 2 spark plugs, meaning the engine required 2 complete ignition systems. Redundancy. If one ignition system failed, the other would keep the engine running. Hinoki noted the size of the cylinders. Each one was enormous compared to Japanese radial engine cylinders. The bore was 5 3/4 inches. The stroke was 6 inches. That gave each cylinder a displacement of 156 cubic inches. Multiply that by 18 cylinders, and the total displacement was 2,804 cubic inches. Japanese engines were typically in the 1,500 to 2,000 cubic inch range. The supercharger housing sat at the rear of the engine, a massive cast aluminum structure containing the impeller and diffuser that compressed incoming air before feeding it to the cylinders. The supercharger was mechanically driven by gears from the crankshaft, spinning at extremely high speeds. American engineers had developed sophisticated metallurgy and machining techniques to build superchargers that could operate reliably at those speeds and temperatures. Japanese engineers had struggled with similar technology. Japanese superchargers worked, but they were less efficient, less durable, and required more maintenance. Hinoki examined the cylinder cooling fins. They were thin, closely spaced, precisely formed. The spacing and design were optimized for maximum heat transfer. Cooling was always a challenge with large radial engines. The rear cylinders ran hotter than the front cylinders because they received less airflow. American engineers had addressed this with careful fin design, with baffles that directed cooling air to the hottest areas, and with tight manufacturing tolerances that ensured consistent cooling across all cylinders. The carburetor was a Bendix pressure injection type, mounted low on the engine. Unlike float-type carburetors that could not handle negative G forces, the pressure injection system could supply fuel under any flight condition. That meant the P-47 could perform inverted flight, negative G pushovers, and sustained dives without the engine cutting out. Japanese fighters with float carburetors would lose engine power during negative G maneuvers, a weakness American pilots had learned to exploit. Hinoki asked the mechanics to disconnect the propeller reduction gear housing. This required careful work. The reduction gear was a complex piece of machinery that allowed the propeller to spin at a lower RPM than the engine crankshaft. The R-2800 engine's crankshaft turned at approximately 2,700 RPM at full power, but the propeller spun at only 2,100 RPM. The reduction gear made this possible through a precisely machined gear train. Japanese engines used similar systems, but again, the scale and precision of the American design was impressive. The mechanics worked for nearly an hour removing fasteners, disconnecting oil lines, and carefully extracting the reduction gear housing. When it was finally removed, Hinoki examined the gears inside. They were cut with extraordinary precision. The gear teeth showed minimal wear despite the enormous torque loads they had to transmit. The housing itself was XP's cast aluminum, carefully machined, with bearing surfaces that were smooth and precise. Hinoki made notes in his logbook. Every dimension, every design detail, every material choice was recorded. His report would go to Japanese Army Air Force Command, to engine manufacturers, to aircraft designers. They needed to understand exactly what they were facing. The reality was sobering. American engineers had not invented revolutionary new technology. The R-2800 used the same basic principles as Japanese radial engines: 2 rows of cylinders, mechanical supercharger, reduction gearing, air cooling. But the execution was far superior. The materials were better, the machining was more precise, the quality control was tighter, and most importantly, the Americans had the industrial capacity to mass-produce these enormous, complex engines by the thousands. Hinoki knew the production numbers. Pratt and Whitney had built over 125,000 R-2800 engines during the war. That was more engines than Japan produced of all types combined. The R-2800 powered the P-47 Thunderbolt, the F-6F Hellcat, the F-4U Corsair, the A-26 Invader, the B-26 Marauder, and several other aircraft types. American factories were producing hundreds of these engines every week. Japanese factories could not match that output even if they had the designs and the materials. Over the next 3 days, Hinoki and his team completely disassembled the R-2800 engine. Every component was measured, photographed, and documented. The crankshaft was removed, a massive forged steel piece weighing over 200 pounds. The connecting rods were examined, each one precisely machined from high-strength steel. The pistons were removed, aluminum forgings with multiple compression rings and oil control rings. The valve train was documented, showing the push rods, rocker arms, and valves that controlled airflow into and out of each cylinder. Japanese engineers had built powerful radial engines. The Nakajima Homare produced 1,900 horsepower from 2,000 litres of displacement. That was impressive power output for its size. But the Homare was notoriously unreliable. It overheated. It suffered from bearing failures. It required constant maintenance. Many Japanese pilots refused to fly aircraft powered by the Homare because they did not trust it. The R-2800, by contrast, was extremely reliable. American pilots routinely flew missions lasting 4 to 5 hours at high power settings. The engine would run smoothly, maintain power, and bring the pilot home. Maintenance intervals were long. Engine failures were rare. That reliability came from superior materials, superior manufacturing, and superior quality control. Hinoki examined the materials used in critical engine components. The cylinder barrels were forged steel, nitrided to provide a hard, wear-resistant surface. The valve seats were hardened steel alloys. The bearings were high-quality roller bearings, precisely manufactured with tight tolerances. Every material choice showed careful engineering and access to high-quality metallurgy. Japan's access to strategic materials had been limited throughout the war. Molybdenum, tungsten, nickel, chromium, all the alloying elements needed for high-strength steel were in short supply. Japanese engines had to be designed around the materials that were available, not the materials that were optimal. American engineers had no such constraints. They specified the best materials for each application and built engines that could operate reliably at high power for extended periods. The supercharger was particularly impressive. Hinoki had spent years working on Japanese supercharger designs, and he knew how difficult it was to build a unit that could compress air efficiently without overheating or failing. The R-2800 supercharger was a masterpiece of precision engineering. The impeller was machined from a solid aluminum forging, with blades carefully shaped to optimize airflow. The diffuser was designed to slow the high-velocity air coming off the impeller and convert that velocity into pressure without losing efficiency. The entire assembly was balanced to micron-level precision so it could spin at over 20,000 RPM without vibration. Japanese superchargers worked, but they were less efficient. They generated more heat. They were more prone to failure. The gap in technology was not enormous, but it was significant. And when you multiplied that small advantage across every system in the aircraft, the cumulative effect was a fighter that was significantly more capable than anything Japan could produce. On the 4th day of examination, Hinoki turned his attention to the rest of the P-47 airframe. The engine was the most impressive component, but the entire aircraft reflected American industrial capability. The fuselage was constructed from thick aluminum sheet, riveted to heavy internal frames. The skin was much thicker than Japanese aircraft skin. It had to be, to support the weight of the engine, the armor, the weapons, and the fuel. The cockpit armor was particularly striking. Behind the pilot's seat was a thick steel plate, approximately 3/8 of an inch thick, weighing over 60 pounds. That single piece of armor weighed more than the entire instrument panel of a Zero. The windscreen was laminated, bulletproof glass, nearly 2 inches thick. Japanese pilots had no such protection. Weight savings had been prioritized over pilot survivability. The armament was equally impressive. The P-47D carried 8 Browning M250 caliber machine guns, 4 in each wing. Each gun had a loaded weight of over 60 pounds, and the aircraft carried approximately 400 rounds per gun. The total weight of guns and ammunition was over 1,600 pounds. That was nearly 30% of a Zero's entire weight, devoted just to armament in the Thunderbolt. Hinoki examined one of the Browning machine guns that had been removed from the wing. It was a beautifully engineered weapon, machined from high-quality steel, with a recoil-operated action that was reliable and effective. The 50 caliber round was devastating against aircraft. A single hit could destroy an engine, sever a control cable, or kill a pilot. Japanese pilots had learned to fear the concentrated firepower of American fighters armed with multiple 50s. The fuel system also reflected American design philosophy. The P-47 had multiple fuel tanks, all self-sealing. The self-sealing technology used layers of rubber compounds that would swell when exposed to fuel, automatically sealing bullet holes. Japanese engineers had tried to develop similar technology, but the materials were not available in sufficient quantity. Most Japanese aircraft continued to use non-self-sealing tanks throughout the war. A single tracer round into a fuel tank would turn a Japanese fighter into a fireball. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By the 5th day, Hinoki had completed his examination. His report was detailed, technical, and deeply concerning for Japanese military planners. The P-47 Thunderbolt represented a level of industrial capability that Japan could not match. The aircraft was not faster than Japanese fighters. It could not turn as tightly. At low altitude and low speed, a skilled Japanese pilot in a Zero or a Hayabusa could outmaneuver a Thunderbolt, but those advantages were irrelevant if the Japanese pilot could not survive long enough to exploit them. The Thunderbolt could absorb punishment that would destroy any Japanese fighter. It could dive faster than any Japanese aircraft could follow. Its heavily armed 850 caliber machine guns could shred a Japanese fighter with a 1-second burst. And most importantly, American factories could produce Thunderbolts by the thousands, while Japanese factories struggled to replace combat losses. Hinoki's report included specific observations about American manufacturing capability, the quality of materials, the precision of machining, the attention to detail in every component, all indicated an industrial base that was operating at a level Japan could not hope to match. Every rivet was precisely formed, every weld was clean and strong, every control cable was properly tensioned. The aircraft had been assembled by workers who had the tools, the materials, and the training to build a quality product. Japanese aircraft production suffered from constant material shortages, undertrained workers, and inadequate tooling. Quality control was inconsistent. Aircraft rolling off production lines often required extensive rework before they were flyable. Combat units complained constantly about mechanical problems, engine failures, and systems that did not work correctly. The Americans apparently did not have these problems, or at least not to the same degree. The report was classified and distributed to senior Japanese Army Air Force officers and to the major aircraft manufacturers. The response was muted. Everyone already knew that American industrial capacity was vast. Everyone already knew that American aircraft were tough and well built. Hinoki's report simply confirmed what was already understood, but there was something particularly demoralizing about seeing the evidence laid out in precise detail. The R-2800 engine sitting disassembled on the hangar floor represented everything Japan lacked. advanced metallurgy, precision manufacturing, abundant strategic materials, a skilled workforce, an industrial base that could mass-produce complex machinery at a rate that seemed almost incomprehensible. Japanese engineers had designed excellent aircraft early in the war. The Zero had been revolutionary when it first appeared in 1940. Nothing could match its combination of range, speed, and maneuverability. But the Zero's design had been frozen in 1939, and improvements had been incremental. The Americans, by contrast, had developed entirely new generations of fighters. The P-47 Thunderbolt entered service in 1943. The P-51 Mustang with its Merlin engine appeared the same year. The F-6F Hellcat and F-4U Corsair, both powered by R-2800 engines, were dominating Pacific carrier battles. Japanese designers had tried to develop next-generation fighters. The Nakajima Ki-84 Hayate was fast and well-armed. The Kawanishi N-1KJ Shiden was competitive with American fighters in performance, but these aircraft suffered from the same problems that plagued all Japanese production: unreliable engines, inadequate materials, inconsistent manufacturing quality. A Ki-84 that worked correctly was an excellent fighter. But many Ki-84 seconds did not work correctly. Engines failed. Landing gear collapsed. Systems malfunctioned. The Americans had solved these problems. Through superior engineering and superior manufacturing, an P-47 that rolled off the production line would work reliably. Its engine would run for hundreds of hours. Its systems would function correctly. Its structure would withstand combat damage and bring the pilot home. Japanese aircraft could not consistently deliver that level of reliability. Hinoki understood the implications. Japan could not win a war of industrial attrition against the United States. Every month, American factories produced more aircraft than Japan could produce in a year. Every month, American training programs graduated more pilots than Japan could replace from combat losses. Every month, the material advantage shifted further in favor of the Americans. The captured P-47 remained at Tachikawa for several more weeks. Other engineers examined the hydraulic systems, the electrical systems, the radio equipment. Test pilots flew the aircraft to evaluate its handling characteristics. The consensus was the same. The Thunderbolt was a formidable aircraft, well-engineered, well-built, and backed by an industrial machine that Japan could not compete against. The test pilot assigned to fly the captured P-47 was Captain Takeo Tanemizu, one of the most experienced aviators in the Japanese Army Air Force. Tanemizu had over 2,000 hours of flight time and had flown nearly every Japanese fighter type. He had fought against Chinese pilots in 1938, had tested captured Soviet aircraft in 1939, and had evaluated British and American aircraft throughout the war. If anyone could provide an accurate assessment of the Thunderbolt's capabilities, it was Tanemizu. On December 3, 1943, Tanemizu climbed into the cockpit of the captured P-47 for his first flight. The cockpit was spacious compared to Japanese fighters. The seat was large, comfortable, with thick cushions. The canopy provided excellent visibility in all directions. The instrument panel was logically arranged, though all the gauges were calibrated in English units: airspeed in miles per hour instead of kilometers per hour, altitude in feet instead of meters, engine manifold pressure in inches of mercury instead of millimeters. Tanemizu had studied captured American pilot manuals. He knew the procedures for starting the R-2800 engine. The process was more complex than starting a Japanese radial. Prime the cylinders, set mixture rich, crack the throttle, engage the starter. The big 18-cylinder engine turned over slowly at first, then caught with a deep rumble that was distinctly different from Japanese engines. The sound was lower-pitched, more powerful, almost menacing. The engine warm-up took several minutes. Tanemizu watched the oil temperature gauge climb slowly toward the normal range. The R-2800 required careful warm-up to ensure proper oil circulation through all 18 cylinders. Rushing the process could damage the engine. Japanese pilots often skipped proper warm-up procedures due to combat urgency, which contributed to engine reliability problems. American procedures were more methodical, more careful. When the engine temperatures were correct, Tanemizu tested the magnetos. Both ignition systems checked good. He tested the propeller pitch control, watching the RPM change as he cycled the prop from fine pitch to coarse pitch. He tested the supercharger control, switching between low and high blower settings. Everything worked smoothly. Tanemizu released the brakes and began taxiing. The P-47 was heavy on the ground, much heavier than any Japanese fighter. The nose-wheel steering was effective but required attention. He taxied to the runway, ran through final checks, and advanced the throttle. The acceleration was impressive. The R-2800 at full takeoff power produced over 2,000 horsepower, and the big fighter accelerated rapidly down the runway. The tail came up at 70 miles per hour. At 110 miles per hour, Tanemizu pulled back gently on the stick, and the P-47 lifted off smoothly. Gear up. The aircraft climbed away at a steep angle. The first thing Tanemizu noticed was the sheer power available. Japanese fighters climbed well, but they had to be flown carefully. Too much back pressure, and the airspeed would decay. Too steep an angle, and you risked a stall. The P-47 just powered upward with authority. The engine pulled strongly at full power, and the aircraft climbed at over 2,500 feet per minute. At 5,000 feet, Tanemizu leveled off and began exploring the aircraft's handling. The controls were heavier than Japanese fighters, but responsive. The ailerons required more force to move, but the roll rate was good. The elevator was well balanced. The rudder was effective. The P-47 was stable in flight, not twitchy or difficult. Tanemizu tried a series of turns. The aircraft turned well for its size, though it could not match the turn radius of a Zero. At low speed, the P-47 would lose energy rapidly in a hard turn. But at high speed, it maintained energy much better than Japanese fighters. That was a significant tactical advantage. American pilots could use the P-47's superior high-speed handling to control the terms of engagement. He tried aerobatics. Loops were smooth and effortless. The engine maintained power through inverted flight without hesitation. That carburetor design made all the difference. Japanese fighters would lose engine power during negative G maneuvers, forcing pilots to avoid certain aerobatic figures in combat. American pilots had no such limitation. Tanemizu pushed the P-47 into a dive. The aircraft accelerated rapidly. 300 miles per hour, 350, 400. The controls remained effective. There was no flutter, no vibration, no indication of structural stress. Japanese fighters would start buffeting and shaking in high-speed dives. Control surfaces would become difficult to move. The P-47 just dove smoothly, accumulating speed with no apparent limit. At 420 miles per hour, Tanemizu pulled out of the dive. The G-forces were substantial, probably 5 or 6 Gs, but the aircraft pulled through smoothly. The structure was clearly built to handle extreme loads. Japanese fighters were stressed for lower G limits. Pulling too hard could overstress the airframe and cause structural failure. The P-47 seemed to have enormous strength reserves. Tanemizu climbed to 20,000 feet to test high-altitude performance. The engine continued to produce strong power. The supercharger was working effectively, compressing thin air at altitude and maintaining manifold pressure. At 25,000 feet, the P-47 was still climbing at over 1,000 feet per minute. Japanese fighters would be gasping for air at that altitude, their engines losing power, their climb rates dropping to a few hundred feet per minute. This was another significant American advantage. Much of the air combat over the Pacific was taking place at medium to high altitudes, especially during bomber escort missions. American bombers typically flew between 20,000 and 30,000 feet. Japanese fighters struggled to reach those altitudes quickly. By the time they climbed high enough to intercept, they were often low on fuel and short on options. The P-47 could climb to 25,000 feet in under 15 minutes and still have plenty of fuel and ammunition for combat. Tanemizu tested the aircraft's armament by conducting dry firing passes. He lined up on a point on the ground and squeezed the trigger. Nothing happened, of course, since the guns had been removed and the ammunition expended. But he could imagine what 850 caliber machine guns would do to a target. The convergence point where all 8 guns aimed at the same spot would create a devastating cone of fire. Any aircraft caught in that cone would be destroyed in seconds. Japanese fighters typically carried 2 rifle-caliber machine guns and 2 20mm cannons. The cannons had more destructive power per hit, but they carried limited ammunition, typically 60 to 100 rounds per gun. Pilots had to be very careful about ammunition conservation. Fire too long and you would run out of cannon rounds and be left with just the machine guns. American pilots in the P-47 had approximately 400 rounds per gun, over 3,000 rounds total. They could fire extended bursts without worrying about running out of ammunition. After 45 minutes of flight testing, Tanemizu returned to Tachikawa and landed. The landing was straightforward. The P-47 had good low-speed handling, and the wide landing gear provided stable ground contact. He taxied back to the hangar, shut down the engine, and climbed out of the cockpit. His assessment was clear and would be included in his official report. The P-47 Thunderbolt was an excellent aircraft, especially at high altitude. It was fast in level flight and extremely fast in a dive. It was tough, capable of absorbing battle damage that would destroy any Japanese fighter. It was heavily armed with devastating firepower, and it had long endurance, with enough fuel to escort bombers deep into enemy territory and engage in extended combat. The weaknesses were also clear. The P-47 was not as maneuverable as Japanese fighters at low speed. It could not climb as quickly at low altitude. It required a long takeoff run, and it was extremely heavy, which meant it required substantial infrastructure. Runways had to be long and in good condition. Maintenance facilities had to be well equipped. Fuel supplies had to be abundant. But those weaknesses were almost irrelevant given American operational capabilities. American forces had long runways built by engineer battalions with heavy equipment. They had well-stocked maintenance facilities with spare parts flown in by transport aircraft. They had fuel delivered by tanker ships and stored in large quantities at forward bases. The Americans had the logistical infrastructure to support heavy, complex, high-performance aircraft. Japanese forces increasingly did not. Tanemizu flew the P-47 3 more times over the following week, conducting additional performance tests and simulated combat maneuvers. Each flight reinforced his initial conclusions. The aircraft was formidable, and the engine was the key to everything. That R-2800, with its 2,000 horsepower and remarkable reliability, enabled the entire aircraft's capabilities. The reports from Hinoki and Tanemizu were compiled into a comprehensive assessment that was distributed to Japanese Army Air Force Command in late December 1943. The assessment was thorough, technical, and deeply pessimistic about Japan's ability to counter American air power in the long term. The report noted that the R-2800 engine represented a level of engineering and manufacturing sophistication that Japan could not replicate with available resources. Even if Japanese engineers could design a comparable engine, which was theoretically possible, Japanese factories could not produce it in meaningful quantities with the materials and machinery available. The report also noted that the P-47 was just one of several American fighter types powered by the R-2800. The F-6F Hellcat and F-4U Corsair both used the same engine and were devastating Japanese naval aviation in the Pacific. Hellcat pilots were achieving kill ratios of over 10-to-1 against Japanese aircraft. Corsair pilots were achieving similar results. These were not marginal advantages. These were overwhelming technological and industrial superiorities that were changing the outcome of the war. Japanese Army Air Force Command responded to the report by accelerating development of new fighter designs. The Nakajima Ki-84 Hayate was pushed into production despite ongoing reliability problems. The Kawasaki Ki-100 was developed as an emergency measure when German engine technology proved unsuitable. New tactics were developed to exploit American weaknesses, focusing on surprise attacks, superior numbers at the point of contact, and kamikaze tactics when conventional methods failed. But none of these responses addressed the fundamental problem identified in Hinoki's report. Japan could not match American industrial production. Every month, the United States produced more aircraft, more engines, more weapons, more ammunition than Japan could produce in 6 months. Every month, American training programs graduated hundreds of new pilots. Every month, American shipyards launched new carriers, new destroyers, new transports. The material imbalance was growing wider, not narrower. The captured P-47 remained in Japan for several more months. Additional engineers examined it. Additional pilots flew it. Detailed technical drawings were prepared. Photographs were taken of every component. The aircraft was eventually damaged beyond repair in April 1944 during an American bombing raid on Tachikawa. The engine, however, survived and was preserved for continued study. Lieutenant Paul Gambonini, the original pilot of the P-47, spent the remainder of the war in a prisoner of war camp. He was captured after being forced down near Wewak on November 2, 1943. His aircraft had suffered engine damage from anti-aircraft fire, and he had no choice but to land in Japanese-controlled territory. He was taken prisoner, interrogated about American tactics and capabilities, and eventually sent to a POW camp in Japan. Gambonini survived the war. He was liberated in August 1945 after Japan's surrender and returned to the United States in September. He never knew during his captivity that his aircraft had been transported to Japan and thoroughly examined by Japanese engineers. He learned about it years later when researchers tracking captured American aircraft discovered Japanese documents describing the evaluation of P-47, serial number 42-8877. Yoshio Hinoki continued his work as a propulsion engineer throughout the war. He examined other captured American engines, including the Allison V-1710 from a P-38 Lightning and the Wright R-1820 from a B-17 Flying Fortress. Each examination reinforced his conclusions about American industrial superiority. The materials were better, the manufacturing was more precise, the quality control was tighter. After Japan's surrender in August 1945, Hinoki was interviewed by American technical intelligence officers. They wanted to know what Japanese engineers had learned from captured American equipment. Hinoki told them honestly that Japanese engineers had been impressed by American manufacturing quality, but had lacked the industrial capacity to replicate it. Japan had skilled engineers and knowledgeable designers, but the factories did not have the materials, the machines, or the trained workforce to produce aircraft components to American standards. The American officers took detailed notes. They were compiling information about Japanese industrial capabilities and limitations for post-war analysis. Hinoki's testimony confirmed what American planners already suspected. Japan had been defeated not by superior strategy or tactics, though those certainly played a role, but by overwhelming material superiority. The United States had simply outproduced Japan by such a wide margin that no amount of courage or skill by Japanese pilots could compensate. The R-2800 engine became one of the most successful aircraft engines in history. Over 125,000 units were produced between 1940 and 1945. The engine-powered aircraft that flew hundreds of thousands of combat missions. It became the standard power plant for American fighters and attack aircraft in the Pacific Theater. And it remained in production after the war, powering aircraft well into the 1950s. Japanese engineers never successfully developed an engine comparable to the R-2800. The Nakajima Homare, the most powerful Japanese radial engine, produced 1,900 horsepower, but suffered from chronic reliability problems. The Mitsubishi Mk9 was designed to produce over 2,000 horsepower, but never reached mass production. Japanese industry simply could not manufacture large, complex engines with the precision and quality control required for reliable operation. The story of the captured P-47 is not primarily about aircraft performance or combat tactics. It is about industrial capability and the resources required to wage modern war. The Thunderbolt was an impressive aircraft, but it was impressive because American industry could build it, because American factories could produce the R-2800 engine in vast quantities, because American workers had the skills and the tools to manufacture complex machinery to high standards. Japanese engineers who examined the captured P-47 understood this immediately. They saw the quality of materials, the precision of machining, the attention to detail. They understood that these were not characteristics of a single prototype or a small production run. These were characteristics of mass production done correctly, with proper tooling, proper training, and proper quality control. That understanding was demoralizing. It meant that no amount of clever design or tactical innovation could overcome the fundamental industrial imbalance. Japan could develop excellent aircraft designs. Japanese pilots could be well trained and highly skilled. Japanese tactics could be innovative and effective. But none of that mattered if American forces could simply overwhelm Japanese defenses with superior numbers of superior equipment. By mid-1944, the outcome of the Pacific War was no longer in serious doubt. American forces were advancing island by island toward Japan. American submarines were strangling Japanese merchant shipping. American bombers were beginning to attack Japanese cities, and American fighters, many of them powered by R-2800 engines, controlled the skies wherever they appeared. Japanese military planners knew they could not win a conventional war. The strategy shifted to inflicting maximum casualties on American forces, hoping to make the cost of victory so high that the United States would negotiate a settlement rather than invade the Japanese home islands. That strategy led to kamikaze attacks, to suicidal defensive battles, to the deaths of hundreds of thousands of Japanese soldiers, sailors, and civilians. The atomic bombs dropped on Hiroshima and Nagasaki in August 1945 ended the war before the planned American invasion of Japan. Japan surrendered on August 15, 1945. The Emperor's radio broadcast announcing the surrender cited the appearance of a new and most cruel bomb as one reason for accepting defeat. But even without the atomic bombs, Japan's industrial base had been devastated by conventional bombing. Its military forces had been shattered by years of attrition, and its ability to continue fighting had been exhausted. The R-2800 engine that Hinoki examined in November 1943 was a symbol of everything that had gone wrong for Japan. It represented American industrial might, American engineering expertise, American access to strategic materials, American ability to mass-produce complex machinery. It represented the gap between what Japan needed to compete and what Japan could actually produce. When Hinoki stood in that hangar at Tachikawa, measuring the enormous Pratt and Whitney radial, documenting its weight and its specifications, he was documenting the physical evidence of Japan's impending defeat. The engine weighed 2,400 pounds. A complete Zero fighter weighed 5,500 pounds. That comparison told the entire story. American designers could build a fighter around an engine that weighed as much as half a Japanese fighter because they had the power, the materials, and the industrial capacity to do so. Japanese designers had to build fighters that were light enough to be powered by engines half as powerful, and those fighters sacrificed protection, armament, and durability to achieve that lightness. The captured P-47 Thunderbolt and its massive R-2800 engine showed Japanese engineers exactly what they were facing. Not just a good aircraft, not just a powerful engine, but an industrial system that could produce thousands of these aircraft, that could supply them with fuel and ammunition, that could maintain them in the field, and that could replace losses faster than combat could inflict them. That was the lesson of the captured P-47. Not that American aircraft were unbeatable in single combat, though they were certainly formidable. The lesson was that American industry was unbeatable in a war of production. Japan had started a war with a nation that could outproduce them by a factor of 10 to 1 in aircraft, 20 to 1 in ships, and 100 to 1 in some categories of war material. The engineers who examined that P-47 understood the implications. The pilots who flew it understood the implications. The military planners who read the reports understood the implications. By late 1943, everyone involved in Japan's war effort understood that the material balance was overwhelmingly against them. The only question was how long Japan could continue fighting before the inevitable defeat. The answer came less than 2 years later, when Japan surrendered and American occupation forces arrived. The war that Japan had started with confidence in 1941 ended in complete defeat in 1945. And among the many reasons for that defeat One of the clearest was the industrial disparity symbolized by the R-2800 engine that weighed as much as half a Zero fighter. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.